cord to the computer to save bandwidth. And then I'm going to share you know, this is so ugly. I mean, my handwriting's not terrible, but this is pretty terrible. So that's the term that we have now. And now there's only one redex here. Is there a way for me yet to change my color? There's only one thing I can reduce here. I can only reduce this. That's a redex. That is a lambda term applied to another term. This thing here, that redex itself is not a lambda term. It's an application. This thing is applied to this. So this is, you know, like this applied to this, you know, so like, you know, whatever. M1 applied to M2 or something like that. So that's an application. A redex is an application, but there's no rule that tells me that I can apply an application to, you know, an argument. I can't apply this to that. I can't plug in n first. I got to do reduce by saying, you know, and normally when you're writing beta reduction out, you're supposed to kind of be able to do it in your head. So you should be able to say, okay, go back to black, that this beta reduces to lambda m, and you can label that dot lambda n dot. Now I replace the L by true. M n, whoops, that's an ugly n, but you get the idea. Applied to m, applied to n. And so once again, it's like this is where the parentheses go by default. So now what did I do there? I did how did I get from, you know, from this line to the next line is I did the capture avoiding substitution without showing you all the work. Does anyone want to see all the work? It's really boring. It is replace all the L's in this term here. Let me go to something that's like a much lighter color. Replace all the L's in this term by true. Well, there's really only one L. And so I get lambda m, lambda n, the L becomes true, and then I have the m, and then I have this really, you know, brain damaged n over here. I think I should fix that. Now, that beta reduces again to replace all the m's in here by big M. So I get lambda n dot true big M little n. And now that gets applied to n. And so now then that beta reduces to true m n. And so that's equal to, by the definition of true, lambda x dot lambda y dot x applied to m applied to n, and after two steps of beta reduction, first replacing all the x's in here by m, and then replacing all the y's in here by n, but there are no y's. Well, all right, I'll do it one step at a time just on this first one. That should be the m. Applied to n, so that's a beta reduction. Whoops. Oh, that's interesting. Okay. And so that beta reduces in one more step to M. Okay. So this behaved like an if then else, just like I hoped so. Test applied to true returns M. And then we can do another one and we can say, okay, test or if, whatever he calls it, test of false applied to M, applied to N. Will reduce in many steps of beta reduction and to N. If we did all the individual steps. So this looks like if then else. If the first argument to test is either true or is false, it behaves like an if then else. So any questions about that?
Test behaves like an identity function. Is that correct?
No. The identity function just returns whatever you give it. Test takes 3 arguments. Like if we go back to the previous page, if I can figure out how to get there. Okay. Test is a function of 1, 2, 3 arguments, and it applies the first argument, L, to the second and third arguments. The identity function, let's look at the identity function. The identity function is just lambda x dot, whoop, it doesn't look much like an x. Lambda x dot x, that's the identity function.
Thank you.
Can I ask?
Yeah, go ahead.
Is there a particular order when to kind of expand the terms? So, at some point we took true and we actually wrote its definition out. What I found is, I've tried to do similar things using Peirce's definition of what plus is and using, the numbers as defined as combinators. And do you expand as soon as you can, or should you expand at the last point?
Yeah.
Because if I expand too early, my expansions are so wide, I just get lost. But I don't know which is the right approach.
Right. I think, you want to wait. You could have expanded out true at the same time that you expanded out test here, but it's much easier to manipulate true than it is to manipulate the expanded form of true. It's got 1, 2, 3, 4, 5, 6, 7 characters in it, whereas true only has 3. So it's much easier to deal with true as true here and as here and as here, and now finally, and even here, right, we're still reducing this one to get the big N in there, and now finally we had to unfold it, but it's always best to wait as long as you can. But it also takes a little bit of judgment maybe to figure out why you want to wait. Now, one thing I might want to say here, though, is that we'd like this to be a theorem, essentially, that this is equal to M. But I noticed here that we've got lambda y dot M. And I think this is really only true if M and M are closed lambda terms. In other words, they don't have any free variables in them. Oops. The free variables of M is equal to the empty set, and the free is same thing for the free variables of N. Because here, I mean, we could, let's see, would our algorithm, would the beta reduction fix that? It would, because when it came down here, okay, so we don't have to worry about that actually, because beta reduction would fix that. It would if I was, this means, turns out to be, take this lambda term and substitute M for it and apply the result to N. But when I do the substitution, it's going to look and make sure that M doesn't have a free Y in it. So I guess I don't really need to worry about this, but all the terms for Booleans and numbers are closed terms. They have no free variables. Whoops. So I don't know. Is there any term that somebody would like to look at a little bit more? Like, I mean, what, there's and. So let's see. And is equal to lambda B dot lambda C dot BC false. Okay, so now we want to see. So if you think of these as Booleans, right, they're going to return. So if B is a Boolean that's true, like you want B and C to be true. So we want it to be that, you know, and, oh, it's TRU, and true. I'm just going to start writing this. I really dislike that naming. That should evaluate in some number of steps to true, and of anything else should be false, right? If this thing really behaves like an and, oh, that was a false. I'm sorry. I'm going back. Now we could prove that by evaluating and on true and true. But if you look, if you start to get a little like intuition about how this is going to behave, true applied to anything returns the first argument. So it doesn't, so if B is true, it's going to return C. And then C, if C is true, it's going to return, but if B is false, it's going to return false. And then I guess we'd have to look inside how the C and the false gets, you know. Okay. So do you want to try this one? Or somebody has to tell me.
All right. I feel fine about this one.
Okay. and true, true, let's just do the first two steps. Reduces, is equal to, by definition, of B dot lambda C dot BC false. Applied to T, applied to T reduces to lambda C dot C FF applied to TT. And now if you reduce TT on these in here, you could get back, this is just lambda C dot C applied to TT, which is equal to true. So I took a little bit of a shortcut here by just knowing that it's always the case that, TT M N evaluates to M, and FF M N evaluates to N. So here, TT applied to C and FF just evaluates to the first argument, which was C. So then I end up with the identity function applied to true, and then that's just true. All right, so, let's look at the church numerals. Okay, so for church numerals, first, he assumes we've got these constants, and so all church numerals have this form. They have a lambda S, and then a lambda Z, and then some term down here. And for 0, it's just the Z. And for C1, it's lambda S dot lambda Z dot, and it's just however many S's, one S. C2 is lambda S dot lambda Z dot, and this is kind of unfortunate that the default is that it applies to the left, so we have to actually write down all these parentheses to make sure that we're applying S to the result of applying S to Z. If I left out the parentheses there, it would be S applied to S, which, would be untyped. Okay, so those are the church numerals. Now, why? Well, because if we use numbers that have this form, we can write certain functions that we need to be able to write to do arithmetic. So we can write, for example, the successor function, which he writes as SCC, is equal to lambda n dot lambda s dot lambda z dot s applied to n, applied to s, applied to z. So let's compute the successor of C2 or C1. See, again, I would not call it SCC. What's this naming convention? It should just be suck, is what we normally write, but okay. Okay, oops, I want to apply it to let's say C2. Well, that's equal to this whole thing, lambda and lambda s dot lambda z dot s of n of s of z. That thing applied to C2, which beta reduces to, we play lambda s dot lambda z dot S applied to C2 applied to S applied to Z. Now, like in answer to Simon's question earlier, now I'm looking at this and I'm going like, look, you know, first of all, well, there's really nothing to reduce here except this. So I'm going to have to unfold the C2. But I'm also looking at the front and going like, oh, good, this has the form of a church numeral. We're hoping it turns out to be C3, right? So we say, okay, it's lambda S, lambda Z dot S applied to, and C2 is lambda S dot lambda Z dot S applied to S applied to Z. And now that gets applied to S and Z. And so we can sort of see that, okay, we still got lambda S dot lambda Z dot. And now I plug in S for S, and then I plug in Z for Z, and I get this S remains there, but this whole thing in like 2 steps of beta reduction reduces to S of S of, so I got that one, S of Z, which is equal to C3. So the successor function works. Should I have written out the last?
Could you go over that second to the last line again?
Yeah, okay. Sure. Let me get some different color maybe to point things out. So maybe you mean, how did I get from here to here?
Right. Replacing that.
Oh,
S.
this is just, you know, I should, let me erase it. I mean, it's trivial. It's just equals with expanding, whoops, black. This is just equals because I'm expanding C2. This is just.
Oh, I see.
This is just the definition here of C2.
Got it. Thank you.
So I mean, what I find I stumble on a lot when I was doing things like this and doing plus, you know, C2, C3, is understanding where the parentheses are.
Yeah.
The arguments which I then put in.
In a way, it's almost easier to do this stuff in like a text editor because you can cut and paste. And you know you're not going to make errors with parentheses. I don't know. So do you want to look at plus? Now, I asked you to do define a term for raising one number to the power of another. And it's not an entirely trivial thing. Like, I don't expect you to be able to do that like in 2 minutes. That's a problem you're going to have to think about. But it's probably fair, though, that I show you some of the stuff I showed Jessa yesterday. Which is, if you look at times, what kind of, why is he putting a semicolon at the end of these things? See, that's annoying. Okay, but what's the role of this C0? And the way to think about it maybe is that if you like think about like just the standard recursive definition of 0 times k is equal to 0, and like the successor of j times k is equal to, now what do we want to do here? We want to do k. So what I'm going to do when I do multiplication is I'm going to add k, j plus 1 times together. So I can do plus, assuming I already have plus defined. And I say, okay, k plus j times k. But what would like m to the n, I'm sorry, I want m to the 0. I'm going to do it by induction on the, or by recursion on the argument, m to the 0 and m to the, s of k. And m to the 0 is always 1. And m to the s of k is what? Like you want to do m times m to the k, because k is 1 less than s of k. So now if you kind of like look at this pattern and this definition, you can kind of guess what, I don't know, what is he, let's call it expt should be something. You can think of the application of a church numeral to a function as kind of like repeat this function m times. But if m is 0, just return 0. Is that right? This is the first argument. Yeah. So anyway, this gives you, I think, a good hint of how, and Jess already had this, but there's one part missing here, like this identity, the role that 0 plays in this term is now going to get played by 1. So now I've done your homework for you, but I don't know, when's it due? Today? Questions?
I've managed to get hold of Pierce's 2002 book,
Okay.
and it defines times the same ways you've got there, but as an additional exercise, it says, can you define times without using plus? So what I attempted to do was to substitute what we have for plus as its own definition into the kind of the definition we have there,
Right.
and to go through the steps of reduction. But I wasn't too sure whether that is like, and then to simplify it. But is that, can we do that? So it's
I don't
not
think
the same
that's
as
what he
two
means, though, just by plugging in the definition of plus here. Now I have a term that doesn't look like plus. I mean, so maybe we should write down plus here.
Yeah, so that was like the first point, and then the first step, and then the second step was seeing whether I could then like reduce it bit by bit by bit to simplify it. But
Well,
because it wasn't strictly I didn't have any arguments. I didn't know whether I could do that.
Now, this is his definition. And it seems to me like, you know, okay, so he's doing m times the successor. He's doing the successor m times into n times of the successor with z. Okay. So is there another way to write this down? I mean, there certainly is. See, this is the great fun it was for Stephen Kleene and Barclay Rosser were, you know, two great mathematicians and logicians who were Church's PhD students at the time he discovered this, and they kind of like were racing to figure out, can we encode everything we need to do all of arithmetic? Because if we can, then we've kind of got it. And then he has is zero, and then using that, you can, you know, you can write, oh, predecessor. He talks about the predecessor. So if you have the book, the actual book, does he talk about predecessor in his notes? In any case, predecessor, I once took when I was an undergraduate, I took a theory course at SUNY at Albany, and they, no, it was a master's level. It was a graduate course. And this woman said, you know, Mir Bielbaum was her name, and she professor there, and she had us learning lambda calculus, and she was like, okay, now go encode the predecessor function. And this is one that they almost gave up on. Like, they could not figure out how to do the predecessor. It was really hard. And if you look at the encoding in the book, they have to use pairs. They kind of like use a pair to remember the second element of the pair is going to be the one less than this one. And then they keep swapping them and then reducing this one and then swapping them. And it's crazy to figure out how that works. But it's not so much that you need to know, you know, like these definitions. Yeah, you should probably know these definitions, but, you know, but the fact is that by having this ability, you can encode all of mathematics in the lambda calculus, all the arithmetic operations that we want to do. Okay, so the next topic is recursion. I don't know. Do you want to move on? This one is a kind of a favorite one. Yeah.
Can I just go back to my question though? I mean, you wrote out what plus was. So my question was, could we have taken that definition, plugged it into replacing that in the times part where it is, getting rid of CO with its own
putting it right here and plugging this, if it has parentheses around it, in there. Yeah.
And then applying reduction terms to that to try and simplify it.
Oh, it will work,
down.
Sure. That's just like, you know, that's identical. He's thinking of, I think he's thinking of, see, like, you know, this is crazy. There was like this, I don't know, he at one point had been part of the math department, and then he kind of got like booted out. But his whole thing was that the geometric, and I never, no one ever really got it, but he would claim that this definition of times is essentially iterated addition. So, you say m times n, and what you're doing is you're going like n plus dot 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 plus n m times, right? But he was saying, no, this should be a geometric notion of multiplication, is that m times n is, like if m is, whatever, some kind of matrix, and n is like, like let's say 3 long, is going to be equal to something that looks like this. And he was always on this campaign against the whole math department that they didn't get that this is different from this. And so maybe it's possible to do some kind of geometric thinking, like a different, I don't think he means, can you define it without plus? I don't think he means like just, substitute this one in. I think he's thinking like, is there a kind of a different way of doing this?
And that's the difficulty I had with it, because it's then going back to like the intuition and of doing it an alternative way.
Yeah, I don't really
within
know. I mean, I guess, it's a fun thing to think about, but if he doesn't have the answer in the back, I don't know. You could go ask. I don't really know what he was thinking there, because I did notice in some of the answers, like he was like, oh, can we do equals, I think.
He does keep two solutions,
and you can use
I haven't been able to reduce it down to those solutions yet. So that's where I'm struggling with whether it's a completely different approach he's taken.
I don't know. I don't know the answer. So like, he defines greater equal somewhere in here as some kind of lambda term. And then, he says, oh, how about if you define EQ? And you could use the if term or the test term. So you could say test. Okay, so, so you could say, okay, it's, come on. Lambda m dot lambda n dot. And we already had and, so we have and then here you just say test greater equal m n, and then you test, oh, this is GE, and m. And that was the first thing that came to my mind, because we have if then else, so why not, and we have greater equal, so why not do this? And so if you look in the back on his answers, though, on the equal problem, he basically says, oh, a really easy way to do it is this, but here's what I was thinking of. And he was thinking of something more complicated. So I don't know what he meant by that plus question. But it's, it's an interesting thing to think about maybe, and you'll come up with a good answer. I used to do a lecture in 3015, which I always called like what McCarthy doesn't know. And so who's John McCarthy? Anyone know? Philip, speak up if you know.
I do, but I have to run pretty quick because I have a student waiting for me.
All right.
Okay. Okay. Um,
All right. Anyway,
so
John McCarthy
I
was
got to scoot.
the inventor of Lisp. And McCarthy, and it was, Lisp was essentially neck and neck. The first higher level programming language was Fortran. And McCarthy was at Dartmouth University, and he read Church's notes, and he said, I know how to implement this. But he did not know how to do recursion using fixed point combinators. So he added this construct called defun, and then you give the function a name, and then there's a list of arguments, and then there's some body. And then you could have, you could down inside here, F could be in the free variables of M. So you could do recursion, Oh God, what's happening there? So you could do recursion down in here by mentioning F again. It's recursive if F is in M. Now, he had to add this defun because he didn't get the point that you can use fixed point combinators. And so first you can look at this term called omega. And omega is lambda x dot xx applied to lambda x dot xx. And the thing is that if you do a step of beta reduction on this, so you go over here, you take the body, so this beta reduces to, I'm sorry. I'm used to substitution notation that comes after instead of before the thing you're doing the substitution on. So this would say replace x by this, which is lambda x dot xx in the term x applied to x, because this is the body. But then that's just equal to lambda x. It's just equal to omega again. So omega has this horrible feature or this wonderful feature that it reduces to itself. But it's also the case that this still has a redex in it. There's still a read. So there's always, so omega is a term that will not terminate. There's no normal form. And a normal form is when you get to a form of a term where there's no more redexes. So we say, like over here, a term is in normal form if it has no redexes. So omega has no normal form. I don't know if I can write down here. What's that green line? Oh, whoops, that's not omega, that's lambda. I guess I could write it up here. It just runs forever. Okay. Now, in the book, he this is interesting. Okay, so he fixed his notes. The notes are wrong. He says this is the Y combinator, but this is actually something called the Z combinator. And so let's look at this. Z is equal to, I think it's Z, lambda F dot lambda. Oh, and then you've got two terms that are rather long, lambda F dot F applied to lambda Y dot XXY applied to the same thing over again. So this one is kind of nice, I guess. Where's my Y's coming from, though? Did I miss that? No, there they are. Okay. This one's kind of nice because I think this one has the fixed point property, and you only do forward steps of beta reduction, whereas there's another one called Y, which I used extensively, but you know, after you write something down 100 times, you remember it. So let's prove that. What is the fixed point property? We say F has the fixed point property. If for every M, F applied to M evaluates to, in some sense, is equal. Now, there's other things here. It could be beta equivalence, but it's equal to M applied to F applied to M. So what we'd like to do is show that Y, for example, or that Z has the fixed point property. So when you look at this, though, you can sort of see that, okay, it's kind of like unrolling itself. It's unrolling the body. And then this is going to be useful as a way to write down recursive functions. So you can say, okay, so theorem. Oh, let's say Z. Okay, so ZM is equal to, and God, it's worse than the Y combinator. So what is it? It's lambda F dot, maybe we can, I'm sorry. Yeah, it's lambda F dot lambda x dot, somebody tell me if I'm getting this wrong, f x, oh, lambda y, f applied to, I'll just look at it. Yeah, lambda y dot x x y applied to lambda up the lambda x. I just need to copy that thing. I wish there was a cut and paste in here. Lambda x dot f applied to lambda y dot x x y. I guess I got to move this thing out of the way. And so then it's this whole thing applied to M. That's the unfolding. This is by the definition of Z. So now then, that beta reduces to, get rid of this F. Now, I'm flying blind here because I don't remember this proof exactly, and replace the F by M. So we got M applied to lambda y dot x x y applied to lambda x dot f dot lambda y dot x x y. Oh, that's not an F, that's an M. Somebody needs to call out. Come on, Finley, you're not paying attention. Keegan, correct me. Help me. This is okay, so that's where we got to. So now let's replace X. So look, we're getting there. We got an M here. If we do the next beta reduction, we've got an M in front. So this goes to like this, beta reduction. Now we got M in front, and we've got this where we replace all the X's. So we say that's lambda y dot. Now the X becomes this. This thing again, right? Because it's XX, so lambda x dot m applied to lambda y dot x x y. So now then there's that, and then this whole thing applied to y. Did I mess up? Okay, so now I want to do well, maybe this is not the one that goes forward all the way. He didn't prove this in there, did he? Now I'm thinking somehow I need to get back Z. And one way to do it is to do a backward step of beta reduction where I abstract out of this whole thing here, M. So how do I do that? I say, okay, lambda f, I should have done this for the y combinator. It doesn't have so, it's not so big. Dot, and I'm gonna put something in here, and then I'm gonna apply that to M. And every place there's an M in here, I'm gonna replace it with an F. So then I got lambda y dot lambda x dot f lambda y dot x x y lambda x dot f, and I need to move that stuff over. Lambda y dot, oops, x x y. I'm a little bit worried. What is this extra y doing around here? Okay, and so now then I apply this thing to M. Now, does this look at all like Z? Lambda F oh, maybe I should have reduced. I feel like I've made an error. Somebody speak up. Tell me where the error is. I think I made an error.
It looks like the lambda y should have
This one?
had m applied to it. Yeah, the outer one.
Okay, well, here's the M. So the
Because
M
then it looks like it would have been right.
lambda y. This is the M. Is that what you're saying? So I took this and I applied it to this. And so I replaced all the X's in here, which there are two, by this. And so I think I did mess it up. So this becomes M. There's my M. And then it's got a lambda y. And then this is 1x. And then this is another x. Oh, I see. I just, there is no extra y at the end. I just, somehow that got in there. There's 1x. There's another x. Oh, there is a y after that, right? Oh, this is not going well. Because I've got lambda y dot xxy. Ah, I know what I can do here. Okay. Why can't I get it black? Okay, black. Okay. Okay. I hate to erase that next line, but I think I'm going to is, well, no, I can do it now. I started to tell you about this rule before, and there's an additional relationship. There's additional what Barendrecht calls a conversion, which is called eta conversion. And can I insert a page here before the one that I'm working on? Yeah, I think I can. So I need to tell you about eta conversion. So we say that lambda x dot m applied to x is eta convertible or eta equal to just m if x is not in the free variables of m. So, I mean, if you think about this, this is like you know, it's a little bit like uncurrying or you know, removing you know, unnecessary arguments like in Haskell. Suppose I had like, you know, f of x is equal to, or let's say y, so we don't get variables clashing with one another. I can't see the time. Does anyone know how much time do we have?
We're over.
It's about
Oh yeah, we're a bit
15
past.
after.
Oh, okay. I'm sorry. So anyway, let me see. If I then said like, okay, lambda x dot f of x and applied that to like 7, I'm going to get f of 7, which is equal to 8. But I would have gotten exactly the same thing by just applying f to 7. So this thing here, it's kind of useless to wrap a lambda around it. And so that's what the eta reduction rule says. And so just because we've come this far, let's go back over here. I think we need, if we do an eta reduction, we can get rid of, and I can do it now. I probably should have done it before. But now I can do an eta reduction to get m applied to lambda f, and I'm going to remove this lambda y and the y at the end. It's okay to do it now. It just seems like it probably would have been simpler to do it before. And that's equal to m z m. So that completes the proof. The Y Combinator is a little bit easier to do. Now, what does he say here? This one works for call by value. This thing here, Z, I'm not sure, maybe it's not called Z, but I think it is call by value, which means that you evaluate your arguments first before you evaluate the body. And this one works to generate recursive functions in a call by value setting, whereas with a call by name setting, you don't evaluate the arguments first. You plug them into the body. And so there's different fixed point combinators. We'll continue next time maybe with just showing quickly how you can define, like he goes over it in here on the factorial function. I don't know, maybe I'll try to make a little side video of that. Okay, sorry I went over. Any questions?
No.
All right. I guess I'll see you next week, and I'll put up some more reading in the meantime. It seems like I'm lagging behind the reading, you know, a little bit, but I don't know how to catch up. Maybe I give you a programming assignment and don't do any more reading. All right. Talk to you later. See you later. Bye.
Thanks.